In this video, we're going to talk about derivatives being a rate of change. I wrote rates of change, but a rate of change? Sure. Okay, so what we're talking about is that when you have a function, right, and we take a derivative, what we're really doing is we're seeing how y changes in relation to x, but the d means instantaneous change. So at any moment x, so at a specific x, we can see that this change will be a number. Okay, and what that number is in this instance is it's saying that that number is showing the change in y per x. Okay, well, we can do that with any function. So if you had a cost function, a weight function, temperature, elevation, pressure, whatever it's dealing with, what we can do here is whatever variable is on this side is the top. Whatever variable is the independent variable is going to be the bottom, and that will show you what it's representing. Okay, so I'm going to write a couple of different equations and show you how you would interpret each of their slopes. For this first example, we're going to look at a cost function. And cost functions are usually capital C of x, and I have written y equals C of x, but let's talk about the derivative. So the derivative, the C prime of x, would be, now you might write dy dx, but what I really want you to think about is how this cost function works. So how it works is that x are the number of items made, and what comes out, this y or c, if you will, is the cost. So if I'm running a business and I want to sell and make t-shirts, then maybe x is the number of t-shirts I made, and that's my cost in making those t-shirts. Okay, so here instead of writing dy dx, I'm going to actually write dc dx. All right, so what this derivative, dc dx, is measuring is it's saying how the change in cost per x. So in this case, change in cost per shirt made, okay? Or if I was selling, I don't know, slushies, or you name it, right? Whatever my product is. So change in cost per product made. Now, the interesting thing is that it's going to change, possibly, depending on our x value. So what happens is that at a specific x, it will tell me what the change in cost is. Okay, so maybe when I am making 100 items, my change in cost is 50. Maybe when I'm making 1,000 items, my change in cost is 25. It'll just depend. Okay, now just to practice this one more time, because it doesn't have to be a cost function, it could be anything. It could be population. So if we had a function p of t where this is going to give me population over time, and of course we need to know parameters of, is the time years? It probably is the population in thousands or millions, whatever it is. Okay, well here when I take the derivative, what that derivative is going to represent is change in population per year. Per time, per year, whatever it's measured in. Now, the interesting thing is that this is called the growth rate. So if I have a population function, the derivative is the growth rate. And again, that growth rate may change depending on what year I'm looking at. Maybe in 2010, I had a growth rate of 1,200 people per year. Maybe in 2015, I had a growth rate of 20,000 people per year. We don't know. That's what is dependent on the equations themselves. But this is how we interpret what it is representing. So it's not just instantaneous change. It's instantaneous change at a specific time, or at a specific t-shirt, or at a specific value. All right, so that is my introduction to the derivative as a rate of change.